Aloha, this is RBrewer with the Hawaii Department of Health. This is a recording of a presentation I gave at the 10th World Conference on Sampling and Blending in Kristiansand, Norway. It was held between May 31st and June 2nd, year 2022. The title of the presentation was Fake Data, the Need for Theory of Sampling Concepts in Environmental Research and Investigations. This presentation was really an introspective look back at how we've been doing in sampling and investigations in the environmental industry over the past 30 years and ways we could improve them. This conference was mainly attended by experts from the mining industry. They do a lot of sampling in that industry, as well as other sampling intensive industries, including the agriculture, pharmaceuticals, recycling. There were only a few of us here from the environmental industry. I think as I give this presentation, you might begin to understand why. We published a paper, it's a peer-reviewed paper as part of the conference with the same title. Here's the reference to it. This paper goes into a lot more detail than what I'm going to go over today in this presentation. Some of the guidance on theory of sampling that's been published by Hawaii Department of Health is summarized in our technical guidance manual, most recently updated in 2021. So you can see here a breakdown of the main aspects of the guidance on systematic planning of environmental investigations, sampling theory, soil and sediment sample collection, field implementation. We spent a lot of time on that. As I've talked about before, one of the few state agencies, or even government agencies, I think, that actually does their own field work. Also, this section is now on application of theory of sampling to collection of surface water samples, groundwater samples, indoor air, and soil gas. Subslab vapors especially. So you can see a list below recorded webinars, and there's attachments to other training series presentations we've done as well as research papers. Some upcoming guidance on environmental investigations being published in China. I've mentioned this before. I've been working with the Chinese Academy of Sciences, Dr. Sung Jing there, since 2016 on this guidance, environmental characterization and assessment of contaminated soil and sediment. It should be published sometime later on this year. It's finished the drafts anyway about 2 years ago. I've been going through some pretty intensive peer review and government agency review in China. We broke it up into 3 parts. First is a quick fact sheet, just a few pages with a lot of pictures to give a basic idea of past issues and the general approach. The second part is an overview of what we refer to as decision unit and multi-increment sampling methods in general. Pretty concise, about 50 pages, meant for just if you have an hour or so to read it. And then a series of detailed appendices on lots of different topics, theory of sampling, problems with discrete sampling methods, implementation of sampling in the surface, subsurface samples, VOCs, laboratory, and such. Hopefully that'll be out by the end of the year 2022. We spent a lot of time at the conference just discussing the differences in scientific progress in the commodities industry versus the environmental industry. So I like this comparison of confidence versus knowledge in the field. I got this off the web, so I'm not sure who the original author was. But initially, when we start off in any subject, science related or otherwise, you may think we know everything pretty quickly as soon as you learn about it. As you start to think about it more, you realize there's probably more to this than I thought. And then it can get really confusing. Oh, I'm never going to understand this. Then after a while, though, it starts to make sense, and there's kind of an aha moment. And it's a pretty painful process. We semi-joke about going through the 5 stages of grief as you go through this process, but that's pretty much where the commodities industry is now. They're at that aha moment. They went through a painful process of looking very deeply at problems in their industry, especially starting in the 1950s. By the 1980s, they had got the sampling approaches down pat pretty well and having much less problems. In comparison, the environmental industry, as we'll discuss here and have discussed in other issues, we're still kind of stuck at that I know everything initial step. And we talked about in other presentations I've given, the cognitive dissonance hurdle. How do you get over this and admit that you do have a problem first? And then let's think about, why are we stuck with these problems? Why can't we make a change? And how, why can't we move forward? That's something I want to talk about today, and ways we are moving forward now. When comparing the commodities industry and environment industry, it's really the different motivations, but the same question. And ultimately, what we're trying to get to in these sampling intensive industries is what is the mean concentration of X in Y. So in the commodities industry, these are industries like mining, agriculture, recycling, pharmaceuticals, and even oil and gas. And here, several decades ago, then they developed and started using more of a correct use of what we refer to now as infinite element or multi-increment type sampling methods to test these type of commodities. In this case, a single large sample is collected from multiple points within a designated decision volume of the targeted media. So think of mining. In the mining industry, a company might discover a gold deposit. So they dig all this up, they grind it up into small bits and pieces. Then they, say for a 20,000 ton stockpile, someone has to go in and collect a single sample. Then they're going to estimate the mass of gold in that stockpile of crushed up gold ore. Then they sell that stockpile of crushed up gold ore to some processor, probably in another country. They actually go in and extract it. They find out exactly what the mass of gold in that stockpile was. So they find out if they have any errors pretty quickly. It's very similar in the agricultural business where you're testing large stockpiles or silos of grain, looking for fungus or other problems, or in recycling, catalytic converters, looking for recycling precious metals from those. Or even pharmaceuticals. How do you know you really have 200 milligrams of such and such medication in this pill that you're taking? So all these industries use this infinite element type sampling methods, which we'll talk about in more detail in a minute. In the environmental industry, the only part of the industry that does this are people that test indoor air. So we'll talk about this again in a few minutes. They've been using correct methods of sampling. They don't necessarily refer to it as infinite element sampling methods, but they've been doing this for some decades. In testing of soil, groundwater, soil vapor, things like this, there's been an ongoing incorrect use of what's referred to as finite element or discrete grab sampling methods. And in this case, multiple small samples of the media are collected from single points and then independently analyzed. And this can cause a lot of problems, as we'll discuss here in a few minutes. This is referred to as the theory of sampling. It's really completely overlooked in the environment industry. It was initially. And there are a lot of books published on this, especially by the mining industry, testing of particulate matter, like crushed up ore. Same thing again applies to testing of crushed up recycled material, pharmaceuticals, or silos of grain, wheat, and rice and such. So you see some of the books have been published here on the left. These are specific to the mining industry, but the same concepts apply to testing of these media in the environment industry, even air and water. And the two books on the right, keep those in mind. These are really great way to start if you're new to theory of sampling concepts. These are published by AFCO. I'll show you the reference in a minute. So here's the two references here at the top. This AFCO is Association of American Feed Control Officials. This book was written in part by Chuck Ramsey, one of the premier sampling experts in the world, I'd say. And in this case, they hired him just for testing of food crops and livestock feed. But the concepts that they discuss in these two books, either collecting the samples, the first document, or testing the samples in the laboratory, second document, really apply to all these types of, or again, what we refer to as infinite element media. You can see some of the references below. Chuck's if you haven't ever taken this class, it's an eye-opening experience. I think I've taken it 5 or 6 times now. I learn something new every day. We discuss a lot of these same topics in our webinars on our webpage. So there's different types of sampling challenges. It's again taken from these AFCO guidance documents. And here they split the media or things that we sample into 2 different types. One is finite element media. This is what we learned about in high school or college statistics. So in this case, elements are individually identified, randomly selected. So maybe we're thinking about checking the average age of people in a room or something. So we can go in and select individual people, some random sample. So all these people together would be one sample, and calculate mean age and such. Same thing if we're looking at forests, different types of trees, or individual cans of tuna fish, looking at variability between cans of tuna fish or something, or bags of rice, bags of soil, bottles of water, all these contained elements that we individually select and test. Now compare this to what they refer to as infinite element media. In this case, individual elements cannot be individually identified or randomly selected for testing. This type of media would include, say, a pile of flour. You're not going to go in and individually test individual particles of the flour, or even collect one at a time individual particles, or a pile of rice, or a pile of soil, a lake of water, a room of air, subslab vapors. These are all referred to as infinite element media. So a different type of sampling challenge with these. We talk about this in other presentations, but it's a different way of testing finite element media versus infinite element media. So testing of finite element media, this again is classical statistics. It's the easiest media to sample. So by definition, again, media composed of elements that can be individually identified and individually selected at random. Common data quality objectives, DQOs, is variability between elements, or estimates of minimum or maximum, or estimates of means, or other quality control parameters. In this case, the sample is prepared by collecting and independently testing individual elements. It's also referred to as survey sampling in some text. And the only variable, most important variable anyway, is the number of elements selected. This is what we're all familiar with from our classes in statistics. There's another completely different type of media to test. It's the testing of the infinite element media. And this is more risk-based. It's much more challenging to sample. So by definition, again, these are media composed of elements that cannot be individually identified nor individually selected at random. Again, piles of grain, piles of dirt, lakes of water, rooms of air. Common DQO is the mean of targeted decision unit area and volume of the targeted media. So in this case, you designate a very specific area, a very specific volume of the media that you want a data for, a mean concentration for, and you collect a sample from that. But in this case, the sample is prepared by collecting and combining groups or increments of individual elements into a single bulk sample for processing and testing. These are referred to again as multi-increment samples. This term was trademarked by Chuck Ramsey. So in this case, it's more challenging to sample, and variables can include the sample mass. That's a huge issue, especially when you're testing stockpiles of crushed up ore for gold or something, or stockpiles of soil for PCBs. So variables include sample mass, big issue, also the number of increments, the number of points within that targeted decision unit volume that you collect a single sample from, how you collect the sample, how it's processed in the laboratory. It's much more complicated, but it can be done. So these finite element sampling methods that were misapplied in the environment industry, they have been for decades. So some of the early assumptions of contaminant homogeneity and misapplication of finite element, or aka discrete sampling methods. And these assumptions were never tested in the field. But you can see the first one here, the level is assumed to be uniform within an area of contaminated soil and zero outside of it. This is really where the problem first started in 1985, a document called Verification of PCB Spill Cleanup Methods. So you can apply finite element sampling methods, these discrete samples, to some targeted media if it's a uniform. If not, if it's heterogeneous and you move your sample over a few inches or something, get a totally different number, then you can't apply these finite element sampling methods. For groundwater, similar assumption made. Groundwater samples taken in close proximity, say within a few meters, are highly autocorrelated. Dense spatial monitoring runs the risk of redundant data from a 1996 US EPA document. This was never tested in the field. Whoever goes out and puts lots of monitoring wells a few feet apart to look at variability or small scale random variability in contaminant concentrations. Then the third, applying to subsurface vapors, looking at vapor intrusion, the default vapor intrusion attenuation factors assume that the subsurface vapor plume is reasonably homogeneous. This is from a California EPA guidance for the evaluation mitigation of subsurface vapor intrusion to indoor air. So again, you can only apply these discrete sampling methods if it's homogeneous, if the contaminant is homogeneous, and if you collect the sample from a small distance away from the original sample. And for particulates, if the laboratory tests a different spoonful or pinch of soil, if you get the same number, okay, it works. But in reality, this isn't what happens in the field or in the laboratory. There were a lot of early warnings about the application of these discrete sampling methods for environmental media. It's one from 1992. The so-called GRAB soil sample is not really a sample, but a specimen of the material that may or may not be representative of the sampling unit, what we would now call as the decision unit. 1992, 30 years ago, warning against these GRAB sampling methods. Looking at water, the probability is small that any body of still surface water is relatively homogeneous. A single sample point generally is not adequate to describe the physical and chemical properties of the water body. USGS 2006. They understood that even contaminants, say you're looking for bacteria and other things in water, it could be highly heterogeneous and random over small distances. For subslab soil gas, looking at vapors, the paper we published in 2014, spatial variability in subslab soil gas invalidates the use of the US EPA vapor intrusion database for assessment of vapor intrusion risk. We talk about this in other presentations. It's the same problem. These contaminants, whether it's in soil, water, or air, they're not nearly as homogeneous or uniform as the early preparers of environmental sampling guidance thought they were. That's why we have so much problem in the field. We've done some of our own field studies of contaminant compositional within a single, say, spoonful, or between individual particles, and distributional heterogeneity. So compositional heterogeneity is heterogeneity between individual particles. Distributional heterogeneity is just spatial distribution within your area of targeted media. So you see first paper we published, a very detailed field study we carried out several years ago, looked at the heterogeneous nature of contaminants in soil. And for contaminant concentrations and for discrete soil samples, you can see collected just a foot or two apart can be highly different, and it's random. In this case, this is a more extreme example. Some of them aren't this extreme, but it applies to all testing of soil. The data for discrete samples are just by their nature going to be random. It is similar for subslab soil gas. It's seen on the right, the smaller cutout. We did a study in 2017. We collected soil vapor samples within just a foot or two of each other. And again, the concentrations of, in this case, it was PC in the samples were variable, in this case, by a factor of 3. And again, it's completely random. So these larger scale ISO concentration maps, first they show that there's a lot of distributional heterogeneity. So it's not these vapor plumes under slabs, as this picture depicts. It's not at all uniform. And anyone who's collected a lot of samples would know that. So that invalidates the use of these single point subslab vapor samples to make decisions about vapor intrusion. This is a paper published in 2009. There are several others here. So contaminants aren't homogeneous in soil, air, or water. That's really the root problem of a lot of issues we've had in the environmental industry. Here's some of the references. Again, we talk about this in other webinars. First for soil, and then the 2 different papers we published, reports we published for subslab soil vapor. If you're not familiar with the environmental industry, vapor intrusion is a huge issue in the US right now. And I just posted another presentation I gave earlier this year to the Association of Vapor Intrusion Professionals, where we go into more detail on problems of sampling in the vapor intrusion industry. So what are the results of this? The results of misapplication of finite element sampling methods in the environmental industry are these discrete samples. Well, laboratory data are not reliably representative of the sample submitted. So ask any laboratory you send a soil sample to if the data they send you is representative of the sample you sent as a whole. If they had extracted that entire sample, would they get the same number? And I can pretty much guarantee you not a single laboratory technician will say it. Well, it definitely does. That's because laboratories test very, very tiny amounts of soil. You can see in the small handout a pinch of soil. That's the current method for testing for PFAS, perfluoroalkyl substances, in soil samples. ½ a gram. It's a tiny pinch. There's no way, it's physically impossible if you look back at all that work done by mining industry and agriculture industries and such, but it's physically impossible to represent a sample with ½ a gram of soil. You need at least 10 grams, they would say, or 30 grams. So laboratory data not reliably representative of the sample submitted, and the sample is not reliably representative of the area where it was collected. This is a huge problem in the or testing of soils. The laboratory tests different pinch of soil from the jar, they get a different number. You move your sample over in the field a few inches or a few feet, you get a totally different number, and it could be completely random. Maybe it's above your action level, maybe below. We've published papers on this and reports, and have several webinars on it. So ultimately, the error in your data is unknown. And this is what causes projects to be stalled for years and years, that a property abandoned, or someone comes and tests the property later on, finds out it's still contaminated. It's really been 30 years of kicking the can down the road in the environment industry, and I helped kick the can down the road for the first 10 years of my career, which is kind of sad considering I have a PhD in geology. I actually looked into mining and such when I was in school. But we really didn't know any better. We didn't have any options. We knew there were problems in the field. And they knew this too. The people that wrote the guidance early on, there's from 1989, US EPA document methods for evaluating the attainment of cleanup standards. How do you know your data are reliable? They said future changes in EPA policy may invalidate some of the discussions in this guidance in general. The problem is that it's very rare that EPA goes back and looks back at guidance that they've published in details and kind of challenges it in a scientific way. That's just the way EPA operates. It's more up to the states or the private experts to do this. And this quote from 2003 is especially important. We search for a non-conventional statistical sampling method, the theory that takes into account the nature of the particulate materials. These were laboratory people. They knew there were problems in the way they were testing these samples. In 1989, we hit pay dirt, the Pierre-Gilles sampling theory for particulate materials. This is the underpinning for our decision at multi-increment sampling guidance. However, we were only moderately successful at transferring this technology to the environmental industry. This is 2003, 20 years ago, 10 years after someone started raising flags. And why is this? Because we've been doing the same thing for the last 10 years. And there's a high reluctance to change. That doesn't have anything to do with science. And that's interesting discussion in this book, Homo Deus. Highly recommend it if you haven't read it. But it just talks about how when bureaucracies accumulate power, or when they set a path to do something, it's very difficult, if not impossible, to change, at least from the inside. The motivation and the drive to change has to come from the outside. So why was this overlooked? That's, again, at the conference in Norway, and a lot of discussions with other consultants here in Hawaii and on the mainland around the world, really. How do we miss this? Or why are we still ignoring it in the environmental industry, especially compared to the mining industry? So we all start off the same in the mining industry versus the environmental industry. If you just think about testing of soil and sediment, the mining industry, we prepare geologic maps, identify ore bodies, maybe you mine those and stockpile them and such. In the environmental industry, same thing, prepare a site conceptual model with maps of the site. And a lot of times we want to identify source areas of high contamination, just to have more effective remediation. And we may or may not excavate and stockpile this material before we collect samples, make decisions. Skip down to the bottom. In the mining industry, after they get their data, they make some type of assessment regarding the economic feasibility of the project. And then if it's feasible, economically feasible, then they extract the commodity and then market it and sell it and such. A similar approach in the environmental industry. We do an environmental risk assessment. Is the mass of contaminants in this media, the concentration, high enough to pose a significant risk? If so, then we may carry out some type of contaminant removal or isolation. It's a very similar process at the beginning and the end, but it's in the middle where the problems come up. In the mining industry, they refer to it as lots versus decision units. They have lot designation, but then when they go in and collect a sample from this designated area of volume of material, they follow the theory of sampling approaches we talked about before. And in the laboratory, the same thing. When the laboratory gets this sample from the field, they don't just open up the bag or whatever and take out a tiny pinch and test it. They're going to spread the sample out. Usually they'll air dry it, and then they're very carefully collect a large subsample, at least 10 or 30 grams or so. And they may air dry it, sieve it, crush it. They may not even sieve it, depends on the case. and then they very carefully collect a subsample from multiple points within the sample they were submitted to test. And then in their data quality review, then the first thing the person is going to do looking at the data is look at how the samples were collected in the field. Did they collect them properly or not? If not, then that's the end. You start over, recollect your samples. Did they collect the field replicates? And so they would collect replicate samples in the field to check the precision of the sampling method in general. That can highlight problems very quickly. Same thing in the laboratory. The laboratory replicates be collected to test the precision of laboratory subsampling. And then one of the last things is they look at analytical precision. That's important, but that's usually the least source of error in the data. It's usually collecting the sample in the field is where the problems start. They know that. So they go through a very detailed process, and the error in their data is controlled. They'll know within a very small degree of precision or error how far their data could be off. This has very clear business repercussions for these commodity industries, especially if you're getting bad data. I compare this to what happens in the environmental industry. There's really, at least until recently, very poor concept of what a decision it is. We think of exposure areas, but in general, doing investigations in the field, we don't really think of decision units and areas that your sample is supposed to represent. The field sample collection method, just discrete grab, is not very well discussed at all. And how you collect a sample in the field, just put a handful of dirt in a 4-ounce jar and you're done. Same thing at the laboratory. They're not required to thoroughly process the sample and collect a subsample, represent the sample they got. They open the jar, grab a pinch or a spoonful at most, and test it. There's this idea of homogenizing a sample in a laboratory. As a laboratory technician put it to me once, he said, try opening a jar of dirt, sticking a metal rod in it and stirring. It doesn't work very well. If anything, all the fines go down to the bottom. What you grab off the top is definitely not representative of the sample submitted. But that's the way the guidance says to do it, and that's what's done. A big problem with this is the data quality review. So again, in the environmental industry, the way the sample is collected in the field is typically ignored. There's very minimal testing of field sample or laboratory subsample precision. At best, they'll do duplicates. What do you do when your two numbers totally disagree with each other? Instead of thinking, well, gee, maybe I didn't collect the sample properly, they typically just go with the highest concentration and call this conservative. Well, it's not really conservative. It just indicates there's something wrong in the process. And they only do validation of the analytical method in the environmental industry. So the error in your final data is really unknown. It's typically hidden. A big point that I discuss with my fellow regulators is there's no repercussions for the overseeing entity. That's the government for bad data. Compare that to the mining industry. There are very clear repercussions for them if they get bad data, make bad decisions, and say sell you a stockpile of gold, or it turns out to not have any gold ore in it, or much less than you initially thought. It's another interesting discussion we had in Norway, and some of these notes I'm talking about I've added on since the presentation I gave there. The discussions with people there and here in the industry, in the environmental industry in the U.S., and we were thinking about what are the motivating factors in the sampling intensive industries, so the commodities versus environmental. And I remember this point from my college days, the 4 classic tools to motivate change. There was logic, bribery, shame, and violence. How you convince someone to change. And a better way to look at that now would be science, profit, publicity, and lawsuits. When the commodities industry, some of the main motivation to change and ensure their data representative and they're making good decisions, a lot of it is really tied around the science and the profit, and these two are interlinked. So in the commodities industry, again, there's very routine third-party confirmation of sample data. So you know very quickly if your sample data were erroneous with respect to the mass of, say, gold or something in this crushed up ore, because some processing company that you sell it to, they're actually going to extract it. They know exactly how much gold is in there. It's like a third-party confirmation. Same thing with grain. If you find out real quickly if your grain that you sold someone else to make bread or whatever it was actually contaminated when your sampling data said it wasn't, or with ineffective drugs or whatever. So a lot of third-party confirmation for the commodities industry. And again, there are very direct repercussions on the decision makers, the people that said, here's how you go take the sample, here's how you evaluate the data. It could be significant financial loss if they don't do it right. a company goes out of business, you get fired or whatever. So there's this motivation to continually evolve the way you're collecting samples and make it more and more precise and more accurate. Environment industry, that's a big difference. There's rare to no third-party confirmation. So sampling errors in general aren't that obvious unless you're doing remediation, in situ remediation, where, say, for volatile contaminants, and you need to estimate the mass of contaminants present. Talk to anyone who does this in the field, say in situ remediation of PCE contaminated soil or something, and they always assume that the mass of contaminants there is way, way underestimated by the discrete sample data because they know they miss the hot spots and underestimate not only the mean concentration, but the mass in general. But otherwise, beyond this, there's really no third-party confirmation. I guess also someone could go in and test a property in a property transaction. And suddenly they say they use good multi-increment sampling methods. I realize the property is still contaminated, and then a lot of problems come from that. So the issue in the environment industry, though, is the burden of bad data really falls on the consultants and responsible parties, and not necessarily government agencies telling them how to collect the samples. All the negative publicity, the financial loss, the lawsuits, etc., those don't really fall on the people telling you how to collect the samples. That's why in the scale up here for environmental, we switched it from the commodities industry. The main motivations for change, not necessarily science. This stuff isn't that hard. You're collecting samples of dirt, mud, and air and such. But really, it's bad publicity and lawsuits that fall on the people doing the work versus the government agencies that are forcing the change. There are really no direct repercussions a lot of times for decision makers. And not saying that to harass government agencies or myself in general. It's just more of a fact. It's one of the reasons we think why the environment industry is so far behind the commodities industry in collecting good sample data and making good decisions, reliable decisions. So that's the problems. And just at the end of the presentation in Norway, then try to put out some good news. And there is that we can get around these issues now that we're starting to acknowledge that they exist in the environment industry. The theory of sampling applied to particulate matter. We've done a lot of work with that here in Hawaii, and I know it's not just in Hawaii now; it's in China and a lot of places on the mainland. And so that we always start off with a question for any type of environmental investigation or even for commodities. The question is always very similar. It's, does the mean concentration of X in the DU volume of soil, in this case Y, exceed the screening level or risk Z? So the first thing you have to think about is your data needs. So what is the mean concentration of X in soil for the target risk remediation-based decision in these areas and volumes of soil? That's what the remediation or the risk people are going to tell you they need. So the next thing you do is define the decision unit. What's the specific area and volume of soil that you need to test? Well, this is designated based on high risk exposure areas or optimization of remediation, these type of issues. Again, we discussed this in other presentations. I'm not going to go into it in a lot of detail here. So ideally, once you identify this area and volume of soil, the ideal sample, or the ideal thing you could do is just dig it all up and send the entire volume of soil to the laboratory so they could extract it. It's one big mass, one big sample, if you want to call it that. The worst thing you could do is just go in and randomly test a small pinch or a small spoonful of this soil, referred to as discrete samples. Here I've got 1 to 10 grams. Typically, a lot of EPA and other guidance says collect a 4-ounce jar, maybe 200 or 300 grams. But laboratories just can open that jar up and take out a pinch. So really, the data you get back is only representative of that tiny amount, the laboratory test. Worst thing you could do. And mining companies, pharmaceuticals, recycling folks, they would never do this. The way you would really do it is a risk-based approach. You would collect a single, and from our experience and our guidance, you would collect a single 1 to 3 kilogram multi-increment samples from about 50 points. And in 10% of your decision units areas, say for a project, you're going to go in and collect 2 more from each one. So you get triplicate samples from 10% of the DUs just to check your precision. That's the only point of collecting these replicate samples. The concentration of a contaminant for any individual small volume of soil is irrelevant. That's for soil. I think we're getting much better at that here. Well, the The indoor air folks have been doing this for decades. They're the only part of the environment industry that really understood theory of sampling, even though they didn't necessarily call it that. So again, same question, does the mean concentration of X in DU volume of air, Y, exceed the screening level or risk Z? So again, what are your data needs, or what's the mean concentration of X in indoor air during the specified exposure period? That's what the risk assessor would ask the people in the field to go out and get information and tell me that. So what's my decision unit? But the decision unit is the volume of air circulating within the structure during the specified exposure period. Now, typically for chronic risk, we look at years, 6 years or 24 years or something. But for a quick snapshot of what's going on at the place, we can say just look at 1 day volume of air, or a few days of volume of air going through the house. If we assume a default home volume of 244,000 liters, 244 cubic meters, this is the default in EPA's vapor intrusion guidance. So the default 24-hour indoor air exchange volume, assuming an air exchange rate of 0.35 times per hour, over 2 million liters of air a day. Ideally, we'd put all this in one huge beach ball. That the one in the figure is actually pretty much to scale. Send that to the lab, but that's not going to happen. So we have to collect a representative sample. The worst thing you could do is, and no one in the indoor air industry would ever do this, is just go inside the house and instantly open up, say, a 1 liter canister for a second or two, suck in a sample of air and send it to a laboratory. They know that's not going to be reliably representative. So a risk-based approach to do it, similar to what we talked about for soil, you're going to collect a single continuous sample of circulating air during the targeted exposure time. So you might do this by putting a Suma canister in a place in the house, that's occupied. You assume the air is circulating throughout the house and open the Suma canister so it would collect a single sample over 24 hours. Then that 6 liter sample you send to the laboratory will be representative of this 2 million liters that went through that house in a day, is assumed. You can do a passive samplers and other things, but once again, the concentration of the contaminant you're looking for any small individual volume of air within that house is irrelevant. Other webinars and presentations we give, we talk about application of theory of sampling to subslab vapors under buildings. This is to address vapor intrusion concerns, a big issue. We talked about it a minute ago. So again, the question, all the questions are always phrased pretty much the same way. Does the mean concentration of X in the DU volume of subslab vapors intruding the building exceed a screening level or risk Z? So data needs, what your risk assessor is going to ask you is, what is the mean concentration of the contaminant X, say PCE or something, in intruding vapors during the specified exposure period? So the next step is to define a decision unit. The decision unit volume of air of subslab vapors is the volume of subslab vapors anticipated to intrude the structure during the specified exposure period. Same approach, whether it's soil, water, air. Again, in this case, if we look at some of the default vapor intrusion guidance and even building leakage folks, people who do HVAC, but in HVAC systems and energy efficiency as such, would pretty much agree the volume of vapors coming up through the floor of buildings, typically 5 liters per minute in cold climates. And we discussed this in a paper we published in 2014, I think. So 5 liters per minute. Again, let's look at a 24-hour time period. That's about 7,200 liters of intruding vapors per day. You can see a weather balloon we have blown up here in a field study we did. It gives you an idea of 1 day's worth of vapor intrusion, of intruding vapors. Ideally, we send that entire weather balloon to the laboratory for testing. Again, it's too big to test. So the worst thing you could do if you're trying to get the mean concentration of the contaminated intruding vapors over a single day is to grab a single, say 1 liter instantaneous sample from under the slab of the building. Same thing for indoor air. No one in indoor air would ever do this and make a call, but unfortunately it's routinely done in the vapor intrusion industry. A better way, a risk-based approach to do it would be to collect a single continuous sample of vapors intruding a point in the slab over a specified time period. And again, the concentration of individual small volumes, the contaminant in these small volumes, is irrelevant. How do you do this? We have some other presentations. We go into this in detail, but this issue comes up, so I went into a little bit more detail in the presentation. We refer to these as large volume purge LVP subslab vapor samples. Pretty simple. It's similar to a soil vapor extraction test for remediation. You install a hypothetical vapor entry point into the floor of the building. In this case, this is a demolished dry cleaner. The slab was still in place where we did this field study. You hook PVC pipe up to your hypothetical vapor entry point, hook that up to a shop vac to pump the vapors out, add a flow meter on it so you know when these 7,200 liters of volume have gone through the pipe. And as you're purging the vapors from under the slab through this piping, then you have a semicanister attached to it, and it's drawing a continuous sample through that purge volume. And there's lots of details. You have vacuum gauges you're watching and looking for leaks and such. It's not that complicated though. Typically what we do in the field now and in our guidance, you're going to purge 5 days worth of intruding vapors. And in this field study we did, we were purging 6,500 liter purges, but it's roughly 5 days of vapor entry for kind of a moderately cold climate. And if you're doing this at petroleum sites, someone discovered pretty quickly when they blew up a shop vac because the flammable vapors use an air compressor and a guard air type device to collect your LVP subslab samples. Then we discussed this in other presentations. This is from the field study we did in 2014. There's a fallacy, a myth that when you do something like this, where you're going to dilute the hotspot because you magically happen to put your LVP point or your subslab vapor sampling point right on the hotspot. Of course, that's never going to be the case. But we see the exact opposite, as the larger the volume of vapors you purge from the slab, the higher the concentration becomes because you're starting to capture these isolated hotspots underneath the slab that you would have totally missed with these discrete small volume samples. You can see the increase in concentration as we increase the purge volume. This is the mean this is the concentration in each one of those 5 samples. And the mean concentration of the purged vapors overall was continually increasing the more vapors we purged. It started to level off at around 40,000 or so micrograms per cubic meter. This is the way we should be collecting subslab vapor samples to assess vapor intrusion risk. Here's some references. Todd McAllery with Geosyntex, he's been doing this for 20 years. The paper he published in 2010. All we really did to the approach he was doing was add a risk-based volume to it. What volume of vapor should we purge to represent a day of intruding vapors? We have reports, recorded webinars posted to our webpage. So you can apply this. That was indoor air. We did soil, indoor air, subslab vapors. Here's theory of sampling applied to surface water. Same question, just different media. Does the mean concentration of X in DU volume of surface water Y exceed the screening level or risk Z? So data needs, here's what the risk assessor is going to say. What's the mean concentration, say in this case of bacteria? We're often looking for this at beaches in Hawaii. What's the mean concentration of bacteria X in the beach swimming areas? Well, the next step is to define your decision units. We discussed this in more detail in a presentation specifically for testing of groundwater and surface water. But in this case, decision unit is the volume of water within an area typically used by an individual person. So you can see this is Ala Moana Park here in Honolulu. So I split it up into 8 or so, maybe 10 different decision units. Near shore areas where the kids play and they tend to wander back and forth, maybe within a 50, 100 meter area. And then some deeper areas, decision units where the adults might be out swimming or people who can swim better. So we can, once you get out there and look, you'll see the decision units. It's pretty obvious in the field. So these are actually areas, but also actually volumes of water. And the question again is, what's the mean concentration of bacteria within this specified volume of water? So you set it at the resolution, the area and the volume that you need to make a decision. Ideally, again, we'd collect this entire volume of water from each one of these DUs, send it to the laboratory for testing. The worst thing you do is just go up and grab a random jar full of water from a single point within those areas. What's the chance you're actually going to represent that area in general is pretty much nil. From a risk-based standpoint, you can collect a single multi-increment sample from throughout the area and depth of the targeted decision unit. And again, this is same for all media, concentration of individual volumes of water. The concentration of contaminant is irrelevant. Here's how this is done. They actually do this. I always say this would be a great job for someone. collection of multi-increment samples in surface water. So you define your decision units. So what the staff here, consultants too, would do is put a cooler on a surfboard with your sampling equipment. A lot of times it's just a simple jar with holes drilled in the top. It's referred to as an Aloha sampler. And then Chuck Ramsey from Virostat prepares these. So you define your decision unit, you paddle back and forth across the decision unit, and as you stop at so many points, say 30 points or whatever within that area, push the jar down slowly and then pull it back up, and there's your increment for that sample. Then you move to the next point within your decision unit and collect another increment. And when you're done, you've got a nice representative sample for that area. This is also discussed in our technical guidance manual. The one thing we're looking at now, it's more challenging. How about groundwater? What if I move my monitoring well over 5 feet, 10 feet? Or instead of using a low purge sampling methods, if I collected a baler of water or hydro sleeve of water from my monitoring well, would I get the same number? Or probably not. But it's the same question. From a risk standpoint, does the mean concentration of X in DU volume of groundwater Y exceed the screening level or risk Z? So same thing for the data needs, either for mediation or especially for risk. What is the mean concentration of X in, say, drinking water during the specified exposure period? Well, the first thing you have to do is define what drinking water, what groundwater. So maybe your decision of volume. These are ideas we're just now starting to come up with. We haven't really done it that much in the field. Your DU volume might be the volume of water that a child or adult would drink over a target exposure period. Typically for non-cancer concerns, we assume 6 years. If you look at the exposure rate of children, we assume they drink, I think, 0.78 or 1 liter or so of water per day. This comes out to about 1,600 liters of water over 6 years. So that might be your decision of volume of water that we want just one number for. Ideally, maybe you'd purge this volume of water from the well and send that entire volume to the laboratory, where you can't really do that. The worst thing you could do is just take a real small 1 liter or even half liter or smaller 40 milliliter vial sample from that groundwater. What's the chance it's representative of the groundwater around it? Probably not nearly as much as we like to think it is. More risk-based approach, collecting a multi-increment sample, let's put in 30 wells within this targeted area. Well, that's not really going to happen. So a better approach to collecting representative groundwater samples is similar to what we talked about for vapor, subslab soil vapors, collecting these large volume purge samples from a well. Either look at discharge risk, maybe we're going to discharge this water into a storm drain or into the ocean or something, or even collecting samples, core-shaped samples within a single well using a hydro sleeve or something, where we're trying to map out the extent of contamination. These would be like really good discrete samples. These are just some ideas, and again, we talk about this in another presentation. But the same problem exists for groundwater that does for surface water. It does for subslab vapors in the indoor air and for soil or sediment. These are infinite element type media, so we should be applying theory of sampling methods for these type of media to get reliable sample data. That was it. That was the type of discussions we had in Norway, and we continue to have discussions here. So we're making a lot of progress, I think, in the environment industry, but we're still struggling some. And here's a ITRC document, Incremental Sampling Methodology. It was updated in 2020. It's the Interstate Technology and Regulatory Council. This document is going to get a lot of publicity. And I actually helped with the initial document in 2010. There were some problems with it, especially with the statistics section of that. And even the general discussions weren't that well done in 2010. It was just a start. They updated in 2020. So the discussions in this document on discrete sample unreliability, they're actually pretty good. It's a very useful discussion there. They give a useful basic introduction to sampling theory in the document. It's much improved over the 2010 version. Especially they give a really good basic overview of field implementation of soil sampling, collection methods and processing in laboratory and all. That's all well done. Not a lot of details. The group that prepared this, some of them have a lot of experience and some of them didn't in it. But here's the same problem that we had in the 2010 document that you really have to watch for if you try to reference this document for your own work. Is there's a complete absence of and review of the mining industry research, all the statistical databases the mining industry has been compiling for decades and decades, and coming up with the methods for collecting multi-increment samples and such. It's completely absent in the document, unfortunately. It's also a key thing in this application, once again, of discussions of finite element statistical concepts. There's the really poison pill, we call it, for the document, is this erroneous implied requirement for the collection of replicate samples in all decision units, where you collect multiple independent samples to look at the precision, and the use of a 95% UCL for decision making. Well, that's completely related to finite element sampling methods and statistical methods. It doesn't really apply at all to testing of infinite element material. So we point this out in a critique we did of the ITRC document published in 2020. There's also a recorded webinar that you don't need to collect replicate samples in every decision unit. You only do it in 10% of the decision units just to check your precision. You definitely don't need to collect 95% UCLs. Some risk assessors who understand multi-increment sampling and theory of sampling, they do this. They'll actually, they want to calculate a 95% UCL for their multi-increment samples. This is an added measure of confidence in decisions they're making. It's more of a special case. You don't have to do it for every DU, and you don't really need to do it at all unless you're very concerned about your screening level, your cleanup level. You need a very high degree of precision. So all this is just a holdover from discrete sampling methods. Hopefully in the next update of the ITRC document, they'll clear it up. In the meantime, check our critique we did, and especially when the guidance we were publishing with the Chinese Academy of Sciences comes out, check that. That's going to be a really useful document. It's going to be a really good textbook, and there's a lot of discussions of all the problems that we went over here. That was it. It was a great conference in Norway. This group, and these are some of the top sampling statisticians in the world. So if you can afford it and you have the time, then go hang out with them a while. It's amazing what you can learn. So we're still making a lot of progress in the environment industry. Moving along, there's still a lot of work to do. So we ended the conference with just discussing a lot of the topics I discussed in this presentation. And the environment industries, I think we've moved away from this I know everything point. We're getting past our cognitive dissonance issues and realizing there's more to this than we think. And but we can't understand it. There's actually been people who've looked at this in a lot of detail in the commodities industry. And after a while, it's starting to make sense. I think we can get much better guidance. So their next conference is in South Africa, year 2024. So I'm hoping to go to it and talk about some more of the progress that we're making in the environmental industry. So thanks a lot. And my email is at the beginning of the presentation. So as always, enjoy discussing these issues. Thanks.